Yeah. Go.
Thank you. Welcome to my talk. I'm Rafael. I work at Intel. I don't speak for Intel, so whatever I say may not be the official Intel position. Today, I'm going to talk about system suspend and resume, which is kind of an oddball topic for this conference because it has nothing to do with scheduling. So I'm not sure how interesting it is going to be for everybody in the audience, but I will try to keep it high level. We're practical. So, okay, let me start with some recap of the concepts and terminology that is used in this context. Okay, so the system as a whole can be in different states. Like most of the time, it's in the working state in which user code runs. So this is a definition basically of the working state. So the working state is when user code can be scheduled and do work. In the other states, which are referred to as sleep states, the user code doesn't run. It's not scheduled, doesn't do any work. So this is like a difference between the two. Okay, so the sleep states are things like suspend, system-wide suspend, and hibernation. And switching over from the working state to one of the sleep states is a big deal because it basically touches every piece of the system. Like everything has to prepare and then do something. For this reason, the kernel can be built without support for sleep states. So there is a kernel config option that you can use to build the kernel without support. It's called config PM sleep. But if this option is set, then support for system sleep is mandatory. So you basically, if you are a driver developer, you have to remember about this. If config PM sleep is set, you have to support system sleep because this is a whole system thing. So everybody has to participate in it, and there are dependencies between devices and so on. So you cannot just say, okay, I'm not going to support it. Of course, you can make your code depend on not PM sleep, and then it won't be built if this option is not set. But and analogously for hibernation, there is a config option that you can use to compile out support for hibernation from of the kernel entirely. But if it is set, then everything is expected to support it. All right, so in order to get from a working state to one of the sleep states, the whole system has to undergo a transition. They are referred to as suspend and resume. Going forward, I will just focus on system-wide suspend. I'm not going to talk about hibernation today because it's too complicated for a 1-hour talk. And basically, many of the things I'm going to say are applicable to hibernation. Some of them aren't. Right, so when the system is in one of the sleep states, say that I'm going to focus on system suspend. So let's say a system is suspended, then it can be woken up by an event, which is referred to as a system wake up, and then it usually involves an interrupt or similar that triggered by one of the devices, and devices that are allowed to generate those events are referred to as wake up devices. And I'm going to use this term for devices that wake up the system from sleep. Obviously, devices can signal wake up in the working state as well, but wake up devices are the ones that can wake up the system. And keep this thought in mind because this is going to be relevant going forward. Not all devices are allowed to wake up the system, and user space actually decides which are. So that's a Okay. So roughly speaking, when the system is suspending, all activity needs to be stopped and hardware needs to go into low power states, because obviously the purpose of using sleep states is to reduce energy usage. And the wake up devices mentioned before need to be configured for this, sometimes in a special way. And when the system is going back to the working state, all of this needs to be reversed. But the difference is that it sometimes is not necessary to bring everything up to the point in which it was before, because some devices may be left in suspend because they don't need to be resumed and so on. So that's how this goes. And those transitions need to be fast because they may be carried out very often, like in phones, which suspend and resume like every, I guess, a second or something like that, roughly. So the faster they are, the better, generally speaking. And this is one of the areas where improvements are possible or even needed, I would say. Okay.
So, Rafael,
Yeah.
do you consider 0ix as a working state or?
No, it's a sleep state by definition because user code doesn't run in that state.
So that's considered suspend?
It's a system suspend, like one of the variants of it.
Okay.
So every state in which user code cannot be scheduled can be considered as a sleep state, basically. All right. So in the working state, there is power management. There is runtime PM, def freak, CPU idle, CPU freak, things like that, power capping, all of this is used, more or less. And then it interacts with system suspend and resume transitions, obviously, because if it is in use and then systems suspend is started, those things need to be taken into account. The problem may be problem or not a problem. The thing is that system suspend transition may be started at any time. So it's like user space decides, oh, I'm now going to do nothing, so I will suspend the system, and it starts, and then everything needs to be adjusted for it. Like it starts and then goes, and I need to be fast. So it may be necessary to reconfigure devices which have been like runtime suspended, for example, to before entering a sleep state, because runtime PM, which is important to remember, runtime PM always configures the devices to signal wake up if they are capable of signaling wake up, just out of simplicity, because if something gets some like information from the outside, then probably the information is at least worth looking at. So it's better to wake up the device and then process it in the working state. In the sleep state, or in a sleep state, it usually is like we only want a handful of devices to be able to wake up the system. Because, for example, if you use a laptop and you close the lid and you put it into your bag, you don't want your Bluetooth mouse to wake it up while in the bag, right? So usually you will just not allow the mouse to wake up the system. And so if the mouse was under runtime PM before the system suspend, it needs to be configured, in a special way so that it doesn't wake up the system from sleep. That's important. Okay. Obviously, devices depend on one another. Devices, there are parents and children. Like on the PCI bus, there is a house bridge. There are root ports. There are endpoint devices below the root ports. There is a hierarchy. There also are dependencies like consumer producer or consumer supplier, I should rather say, dependencies where one device depends on another one, but not directly. Like it's not a parent of it or not a ancestor, but it depends on the services of that device. So there are device links to represent those dependencies. And device links are kind of on top of the device hierarchy. And so if they are taken into account, all of the dependencies graph is a real graph. It is not a tree anymore. So that adds a piece of complexity to all of this. And obviously, the dependencies influence the ordering of system suspend and resume, because you have to kind of suspend the device before any device is dependent on by it, and the other way around during a system resume. And it can be proven that there is at least one way to suspend and resume the system in a way that avoids circular dependencies. Yeah. All right. So that's a very general like recap of all the concepts involved in all this. Now I'm going to talk about the code. So first of all, there are some code layers which are involved. I chose this photo because of the layers of rock here that you are might be able to see. Okay, so there are 3 layers of code. There is the PM core, which handles generally controls the flow of everything in this. There are drivers, the bottom layer, and between the core and the drivers, there is a layer which I refer to as a middle layer, and this is the code like bus types, classes, device types, PM domains. So the middle layer is expected to handle like things that are common to a group of devices. For example, in a PCI bus type, the middle layer is responsible for handling the interfaces defined by the PCI specification, which are the same for every device. And drivers are expected to handle the pieces that are specific for each device. And in different, so in the ACPI PM domain, for example, the middle layer is responsible for handling the interface defined by the ACPI specification, and again, drivers are responsible for the rest. The way it works is the core invokes middle layer code, and the middle layer code invokes drivers. And it can do something either before invoking a driver or after invoking a driver, or in both places. And drivers, of course, are responsible for device-specific handling. If there is no middle layer code, which is the case for some like for the platform bus type, for example, there is no middle layer code often. The PM core takes takes the role of the middle layer. So in those cases, there are only 2 layers, like PM core and drivers. And the reason of this for this is obviously the division of labor, which and kind of it is related to avoiding code duplication between drivers. Because putting common code into a common place, it allows us to avoid like having multiple copies of the same code in multiple drivers. All right, now each transition is carried out in phases, and there are 4 phases defined or in the code. For every transition. So system suspend consists of 4 phases, and system resume consists of 4 phases. The first phase of suspend is prepare. And it's generally there for in order to prevent children from being added on their devices, because we don't want to like expand the set of devices that need to be handled during the transition that which is ongoing. So the prepare phase is basically for that, and also for general preparation, but this is the purpose of it. In the suspend phase, the activity should be stopped, or at least is expected to be stopped. The late phase was added because of the interactions between the system sleep and runtime PM. So I refer to it as no RPM because in that phase, runtime PM is disabled for every device. And so in order to avoid invoking like runtime PM callbacks concurrently with the system power management callbacks.
Rafael, so I'm actually surprised to read that first line there, that prepare phase is supposed to prevent children from being added.
Yeah.
Because I know for a fact that for PCIe hot clock, we don't do that. It would probably be a good idea, but it's the first time I've heard it. It does make sense, but we're not.
So if this is ACPI based, then this is observed.
PCIe HP.
PCIe HP. Because I was not involved in development of this code, then probably it's doesn't follow all of the rules, but it should because. So the problem with adding devices during system suspend is that the ordering of the transition changes.
Yeah.
And if it changes when in the middle of it, then it is an impossible thing to handle, because you cannot change the ordering of the part of the transition that has already been carried out. So when a new device appears at this point, it may appear under somewhere that already has been handled, and then not really.
We're not stopping IRQs in the prepare phase. That happens later.
Yeah.
Yeah.
So the stopping, that's why this is called no IRQ, which is the next thing that I was going to say. So no IRQ because the IRQs are disabled and before this phase. And actually disabled means that the action handlers are prevented from running. And low-level chip IRQ chip callbacks are still used, but the action handlers are not running. So from the driver perspective, the result is equivalent to disabling interrupts, but it doesn't mean disabling interrupts on the CPU. It's just that. Okay, so system resume goes in a reverse direction. The first phase is no RQ with interrupts disabled in the sense mentioned before. So action handlers do not run. There is an early phase in which runtime PM is still disabled. It is supposed to power up the devices, and then resume is the phase in which the activity is expected to be restarted and then complete with the task to allow new children to be added. There is some overlap between those two phases because in some cases we actually allow children to be added in the resume phase, like for USB, for example, because it is safe at this point because devices. So when you resume a parent, you can at that point start adding children under it without waiting for other devices to resume, basically, right? So this is like kind of a optimization, you can say. And obviously, all of this needs to be coordinated with runtime PM. And there are some PM core, I would say, there is some support for this in the PM core. That's the best way to put it. So the PM core first freezes and unfreezes the runtime PM work queue, which means that during the system, and this is done before the prepare phase. So during the whole transition into a sleep state and back, there is no asynchronous runtime PM going on, just synchronous. And then, so you want you can call inline runtime PM helper functions, but there will be no like async suspend or resume requests. Okay, so the next thing is that the core acquires runtime PM reference on every device, again, during the prepare phase. So you cannot runtime suspend the device during system-wide PM transitions. Yeah, you cannot runtime PM suspend. You can call runtime resume, but runtime suspend will not work. And then before the late early phases, which I refer to as now RPM, the core disables runtime PM for every device to avoid like running callbacks in parallel with each other. And now middle layer code and drivers are also responsible for some things. As far as the coordination with runtime PM is concerned. And they, first of all, need to resume devices that cannot stay runtime suspend. There are devices like that. I will be talking about it later. And if they can stay in runtime suspend, they need to be reconfigured. For example, if they are not allowed to wake up the system, the wake up signaling needs to be turned off, which may not be possible without resuming a device. All right, so that's a recap. Okay. Yeah, so fortunately, our suspend resume code doesn't need to be prevented from collapsing. But it, that's like, yeah, it looks fine, but maybe it could be better. Okay. So one of the things that is done to speed up suspend and resume transitions is to handle suspend and resume of different devices asynchronously. So they, for example, if they need to wait, it's better to let them wait in parallel with each other than wait serially one after the other. So each phase is carried out separately. So the prepare phase needs to complete before starting the resume suspend phase. The suspend phase needs to complete before starting the no RPM suspend phase. And each of those phases has some async handling involved. There are devices that, so okay, there is a lot of legacy in the kernel. There are devices, the drivers, I should say. There are drivers that don't support runtime PM at all, just system sleep. There are drivers that cannot be suspended or resumed asynchronously because there are some dependencies between those drivers and some other drivers, but those dependencies are not expressed in the form of device links, but they are implicit. So there is some ordering in which drivers want to be handled during suspend and resume. And the devices handled by those drivers are referred to as sync, which means that they need to be handled in a specific order with respect to each other. Well, async devices are the ones that are allowed to be handled out of order. But of course, they are handled out of order, but still the non-dependencies need to be observed, right? The dependencies between parents and children, for example, need to be observed. So out of order means out of order with respect to the like canonical ordering, but not with respect to parents or suppliers or similar. Okay, and now there is some say discussion going on. So this is the point where I get to what's actually going on right now on the mailing list. So there is some discussion regarding okay, how to start or when to start the async handling of devices. And there are 4 options for this. Option 1 is something that was first introduced, like when the async concept was started. Then the handling was done after all the preceding sync devices in the canonical order. Obviously, that's not very efficient because because async devices need to wait for all the sync devices before them in the canonical order, and those sync devices may need to wait. So this is not super efficient. The other option is to just start the handling of any of async devices up front, so before any other devices. And they will have to wait for their parents and suppliers, for example, if this is a resume transition, or for their children and consumers if this is a suspend transition. So the handling is started up front, but the devices they need to wait will wait. That's the approach. It turns out to be sort of not very good for platforms where computing resources are limited, because the starting of so basically what happens is that for each async device there needs to be an async work item, which involves creating basically work queue work, which is queued up on a work queue. So the handler kernel thread needs to be started, and so on and so on. So it is quite heavy computationally. And if this is done for all devices that can be handled asynchronously, then there is a spike of activity at the beginning of each phase. And a spike of activity may be hard to handle for a like phone, for example. All right, so there are two other options. So the option 3 is start the async handling only when all of the known dependencies have been met, which requires the tracking of dependencies, because the code needs to look at, is this device eligible for async handling already, or do we need to wait for starting it? So there is option 4, and it is a simpler one, which is like, okay, so why don't we start the async handling when one known dependency has been met, and then it may wait for the other dependencies. And now we are kind of discussing, whether to do option 4 or option 3, basically, because it is not clear if option 3 is any better than option 4 because of some timing things in there. And so it is possible that actually this gets the transitions to the fastest possible, to the highest possible speed, and that doesn't really add any value, but we'll see.
Rafael, I was wondering, why not treat all sync devices as async and then just track?
Because this will break suspend resume on some systems. Because drivers expect things to happen before they are invoked, and there may not be explicit dependency, representation for it.
Okay, yeah, but if you had that, then you could.
Yeah, if you have, if every, so on ARM platforms there is something called firmware devlink, and that feature allows you to resolve all of the dependencies or represent them in the form of device links. So on those platforms, it's basically like all of the known dependencies are represented, and essentially all of the devices could be async. But on the platforms where this is not going on, not really. So, yeah. Now there is one thing that can be, one observation that can be used to speed up, suspend and resume, and the observation is that, okay, we have those phases, and there are reasons for having them, but this actually kind of adds or it could be sped up by making things happen in parallel with each other, even more than it is done now. And for example, if all NoRQ handling is moved to the adjacent phases where runtime PM is disabled, then if anything is to wait in this phase, it may as well wait in parallel with the processing in this phase, which reduces the total time of the transition. So if we are able to kind of merge the phases, then we can reduce the total time of the transitions by letting things, happen in parallel with each other even more. But that's for the future, and I think that it will be platform specific. So on some platforms, it may be possible to do it. To do this on other platforms, there may be problems with legacy drivers, essentially. Okay, so we may be able to speed up suspend resume by doing some nice tricks. So this is under renovation, and then it looks much nicer than it used to, but it's still, unfinished, kind of. Okay, so now I'm going to talk about the integration between the runtime suspend and system sleep transitions, and basically this is, the rest of my topic is about this. And now why this is important, because say a device is runtime suspended before system sleep starts. The transition to system sleep starts. In the majority of cases, it would be very nice to leave this device in runtime suspend, or in suspend in general, without resuming it, because obviously resuming it takes time. And then when it is resumed, it will have to be suspended again, and this again takes time. So in order to avoid, spending this all time on resuming and suspending the device again, that it would be better to leave it in suspend. But this is not always possible, or not. Yeah, this is not always possible, and so some conditions need to be met in order for this to be possible. And now there are conditions that, this is what I'm going to talk about right now. So first of all, we need an opt-in from a driver of the device. That, it is okay to leave it in suspend from the driver perspective. There is at least one case in which the driver doesn't want that to happen, and this is i9-15. On x86 on Intel, because they know that they have dependencies on other drivers and they are not explicit, and so they always want to resume the device. So we need an opt-in from the driver. There are a few different ways to opt in. Maybe I'll talk about it later if I have the time. If not, then I will just leave it like that. The other thing is that the device settings need to be compatible with system sleep. So, for example, if there is a device that can signal wake up, and it has been configured to signal wake up, but it is not allowed to wake up the system from sleep. It needs to be reconfigured during suspend transitions. In order to reconfigure, some devices can be reconfigured without resuming them. For example, this is a PCI device in a D3 hot power state. Then it can be reconfigured without resuming. But if the PCI device is in the D3 cold power state, which means no power at all, then in order to reconfigure it, it needs to be resumed, because only then the registers can be accessed. So this is kind of complicated, and you may ask, like, why bother? Like, why don't we allow all of the devices to wake up the system from sleep? Well, that's not practical for the reasons I mentioned before. Because say you use a laptop and you suspend it and then you put it into your bag, and you don't want it to wake up in that situation, because it may overheat, it may dry the battery. There may be other things that you don't want it to do, like connect to the Wi-Fi networks nearby, for example, while suspend, while in the bag. So there are reasons for preventing devices from resuming the system from sleep. And but if you want your suspend and resume transitions to be fast, then you essentially have a choice. Like, either you choose fast suspend resume, and then you enable all devices to wake up the system, or you prevent them from waking up the system from sleep, and then you need to wait for the processing of those devices. That's simple.
So if we know in advance that we don't want the device to wake up the system from sleep, why do we enable wake up on runtime suspend? Is that enabled at all? Is it for allowing?
It's for allowing the processing of data that can, that comes from the outside. Like, because runtime PM is expected to be transparent.
Okay.
It doesn't mean
for the device to recognize.
For the device to recognize that there is something to process. Maybe so some devices can be configured to ignore the stuff that comes from the outside. Like, for example, Ethernet cards can be configured to just only signal wake up on specific packet types or similar.
Okay, so this is wake up of the specific device, but not wake up of the system.
Yeah.
Okay.
Exactly. There are more conditions beyond that. So one of them is related to the possible expectations of platform firmware, but that I'm going to just flash it, and then I'm not going to spend the time on this. And then there are obviously conditions related to the alignment with the needs of other devices, because if your device is needed by other devices, then it obviously needs to be resumed. And a good example of this is like I2C controllers, which are sometimes necessary to carry out power transitions of other devices. So they need to be resumed to be able to handle some stuff during system suspend and resume. Direct complete is an optimization which one of the optimizations that have been attempted to allow devices to stay in system in suspend over system suspend and resume. And this referred to as smart suspend is another one, but Okay, and analogous conditions apply to system resume. So we may not want to resume all of the devices during system resume. Some of them may stay in suspend and then be woken up by runtime PM if needed. And again, the driver opt-in is required, and it needs to be compatible with wake-up settings. Okay, so the takeaway is that it all is kind of complicated and needs to be handled carefully, right? Because otherwise may misstep and then bad things happen. So what is missing? Unfortunately, different driver opt-in methods are incompatible with each other. Which needs fixing, in my opinion, because then there is a lot of confusion in this. And okay, fair enough. And now, okay, there is a problem with the matching states of devices, like when to resume a device because the state of it is not appropriate. Like I was talking about this. This is mostly related to wake up. The device is not allowed to wake up the system from sleep. It can signal wake up. It has been configured by runtime PM to signal wake up. It needs to be reconfigured. The state of it may not be suitable for system sleep. Okay, and now how to do it? Who should be doing this? This is kind of a open topic for now. PCI bus type and ACPI PM domain handle this for PCI devices and for devices for drivers using the ACPI PM domain. Anywhere else, I would say it's a gray area. Would be nice to do something about this. Device may wake up is a function that tells that returns the return value of this function means whether or not the device is allowed to wake up the system from sleep. So this needs to be taken into account in the first place when deciding whether or not to resume the device, and there are other considerations as well. Okay, there's a couple of rules. I have 5 minutes, so I'm not going to go, dive deep into this. Or observations can be made. This is kind of an interesting observation because basically, if a driver and a middle layer both support runtime PM, then there is no difference between the resume from runtime PM and the resume from during system resume. And in theory, the same set of callbacks can be used for both. Today, the majority of drivers and middle layers use different sets of callbacks for resume during system resume and for resume from runtime PM. Something can be done about this, I believe. Again, maybe with the help of a driver opt-in or something like that. But anyway, it looks like some things can be simplified here. Yeah, so again, the devices that are in wrong states sort of must be resumed during system resume, but otherwise they can be left in a state in which they were. Oh, this is some. The important piece is this: like the decision on whether or not to resume a given device cannot be done in generic code because it doesn't have enough information on the device itself. Like what can be done to it, what's the state of it, and so on and so on. So this needs to be essentially done either in drivers or in the middle layer code that knows something about the device configuration at the hardware level. Okay, with this, there are areas of improvement, at least in principle. Some work needs to be done. Thank you.